I'm Francis Levy, co-director of the Philoctetes Center. Dr. Edward Necessian is the other co-director. And welcome to Mathematics and Imagination, the Geometry of Thought, a much anticipated roundtable which has resulted in a great deal of discussion. Now, the art you see on the walls here is from an exhibit called Photographic Visions, the Art of Seeing, and it ties in with the psychoneurology of the photographic arts roundtable, which occurred here several weeks ago. And many of our art shows are, in fact, as you will see if you've been here before, tie into our roundtable. So this one, on this particular one, we thank Howard Greenberg Gallery for helping with the photographs. That particular photograph on the back is a Robert Polidori photo, and Robert Polidori was here on that roundtable. And Jeffrey Levy-Hinton, the moderator, was also responsible for curating this particular exhibit. Now, please silence your cell phones, and let me just say that all Philoctetes programs are available. People frequently come up to me and say, I really enjoyed the program that you did last week, I'd like to see it again, or I missed last week's program. You can see any Philoctetes program by going to www.philoctetes.org and just going to past programming and hitting the button. It's all videotaped. Also, this evening we have books for sale by our distinguished guests. So now I am pleased to introduce Barry Mazur. Barry Mazur is Gerhard Gade University Professor of Mathematics at Harvard University. He does research in number theory and geometry and is the author of Imagining Numbers, particularly the square root of -15. Dr. Mazur will lead tonight's discussion and introduce our distinguished guest. Thank you.
Oh, well, then I have the honor of introducing Eva Brann. Eva has been teaching at St. John's College in Annapolis for half a century, is the recipient of quite a number of awards, including the Presidential Medal for the Humanities. And I didn't realize I was supposed to introduce Eva, otherwise I would have written a half-hour list of her accomplishments, but one of them is a marvelous book called The World of the Imagination, Sum and Substance. And Eva has taught mathematics and many other things for a long time and is very interested in the interplay between the imagination and mathematics. Is that reasonable?
That's very reasonable.
Okay, the first thing I want to say is I don't think you've had a round table or a course in mathematics before.
Oh, we have.
You haven't. And so therefore the format is up for grabs. That is to say, we can decide how we're going to do it. And the only way to do it so that everybody is engaged is feel free to interrupt, ask a question, ask us to repeat something if we haven't, or
give us an argument.
Give us an argument and make a comment. Okay? Okay, the first thing I want to say, given the fact that I don't know anybody's background in the audience, is that mathematics is in the air. That no matter, it has a bum rap in the sense that it's considered an abstruse subject. It seems to require, people say, years of devotion and learning, and even this funny word, aptitude. But what I want to do is make an end run around all this. And first convince you that no matter what your background is, you have not only absorbed a lot of mathematics, but you may have absorbed some of the deepest mathematics. So here's an example. We say far in the future. And we're happy to say that. And what have we just done when we said this? We have made the metaphor of time as being geometric. The metaphor of time as geometry. Now, once we do this, we have a completely different vocabulary for time. So if you've ever seen, I'm sure everybody's seen graphs. Graphs are part of the air we breathe. So stock market graphs, these are sort of depictions of time where when we talk about them, we don't use necessarily purely temporal vocabulary. We have, so to speak, recruited by this metaphor, time as on a line, time as geometric. We've recruited an immense amount of vocabulary that would otherwise be unavailable to us. We talk about the peaks and the valleys in stock markets. We talk about descents and ascents. And we're perfectly happy to do this. On the other hand, we might go the other way. We might refer to distance in terms of time as light years, or the old-fashioned 2 cigarettes later, that sort of thing. We are perfectly happy to metaphorize one quantity, a geometric quantity, for an algebraic quantity, or the other way around. We can turn geometry happily into algebra when we talk, when we say 8th Avenue and 42nd Street. We're talking all numbers, but we're specifically thinking of a spot in New York City. So our ability to turn algebra into geometry is part of the air we breathe. Our ability to turn geometry into algebra is part of the air we breathe. Our ability to metaphorize things, time, temperature, humidity, as geometric quantities is something that we all do naturally, and this is a long tradition. I mean, there is a it's the 12th century, 13th century bishop of Lyon, Nicholas of Orem, had a treatise that he called The Geometry of Qualities. He's the first guy who invented graphs. So he would see, say, the quality of motion as sort of going in an ascending line, and he would think of that as a way of depicting acceleration. We also talk about speed without blinking an eyelash, and that is an incredible mathematical metaphor. All of these things that we do naturally are have the effect of recruiting a vocabulary that has its root or its anchor in one intuition, geometry, let's say, and applying it to domains that we have that we would otherwise not think of as geometric, or recruiting algebra and applying it in domains that we would not think of as algebraic. So this is the, let's call it the metaphors of recruiting one vocabulary anchored in one intuition, the intuition, say, of vision or geometry, to another, to another domain, or the reverse, the vocabulary of numbers to a domain that otherwise would not be considered numerate. So we've all done this. And these are one of the big leaps, these are some of the biggest leaps of the imagination. And I just want to open the discussion this way to suggest that when we talk, if we do get to talk about other directions, other leaps of the imagination, everyone in this room should understand that we've been doing this. We've been doing this for a long time, and we do it almost without effort. Okay, this is a spiel. Do I have any comments first on that? Or do we? Yeah, Barbara.
I just wanted to add that you're doing a gesture too. I was watching your hands, and when you talked about time, you made a movement from left to right, which is characteristic of writers of Western language, to think of time as moving from left to right and to make that gesture when they talk about time.
Well, okay, so in fact, what you've done is you've reminded us that the body is absolutely essential for most of the metaphors that we're most comfortable with, I think. That's part of it.
That's another way that some communication is quite visual in the way that we use our hands.
Any other comments?
I wanna, I have an intriguing idea. Is this: how come an equation
An equation, yes?
could be equal or beyond a metaphor?
How can an equation...
Would be equal or beyond. When I say beyond, is any expectations.
Beyond a metaphor.
A metaphor. Especially when you talk about dreams, for example.
What?
When you talk about dreams.
Dreams, yes. Okay, so let me take the first part of your question about equations as metaphors. X equals y, and you might say x equals y, or x is metaphorically y. Is that might be the drift of what you're saying? In a way, it is. Let's put it this way. I would say it's also the source of really fascinating metaphors. For example, there are standard equations of hydraulics where the vocabulary is water, pressure, the size of pipes, the speed of water. Water is an incompressible fluid, so you have sort of very, very precise equations which describe that sort of thing. Now, these equations are so useful that you can't just let them live in one domain only. And so when people began to think of electricity, they tried to recreate exactly the same equations, if you wish, but for electricity. Now, for that, you have to talk about, pressure. You have to talk about resistance. There may be a sort of friction, that kind of resistance. You have to talk about various other things, like kinetic energy as well, but in the language of electricity. And one of the templates that early electrical equations had were hydraulic, metaphorical templates. Well, that's electricity going through wires. And Maxwell, who discovered that something happens electrically that doesn't involve wires, in other words, radio, realized, I guess others too, realized that there's a problem if you're going to conserve energy, and there's a kind of, well, basically radio waves. So how is it that radio waves, which travel at finite distance from the transmitter to the receiver — this is totally anachronistic vocabulary if we're going to talk about Maxwell, but anyway, the radio waves move at finite velocity. So if you don't take account of those radio waves while they're neither in the transmitter or in your receiver, but somewhere in the air, you lose conservation of energy. So the only way to take account of it is to maintain stubbornly and dogmatically exactly the same equations that started out in hydraulics, and then had their continued life in the electricity, sort of simple electrical circuits, and now had to account for the fact that a certain amount of the energy was moving through a domain that was not wire and therefore was not part of the structure that the equations were dealing with. And so what he did was he actually used exactly the same letter, even J, for the current that would go through a wire, which itself was metaphorically water going through a pipe, for electromagnetic waves going through space, so as to retrieve, or at least sort of somehow keep up the structure of the equation in this new metaphorical realm. So what you're saying, I think, is absolutely right. I mean, equations not only are themselves metaphors, but they're the seeds of lots of metaphors. Wouldn't you say?
I have two questions. But the first one is, isn't the case that an equation has two aspects? One is what goes into it. Numbers or physical quantities, constants, variables. The other one comes much earlier and seems to me even more metaphorical, namely that it's a kind of balanced lever, so that what you do to one side, you have to do to the other. And if you want to shove everything on one side over on or most of it on the other side, you've got to do that in a certain way, such that the balance is preserved. Now, it seems to me this is a really interesting metaphor, and I think it took a long time for people to recognize that one could do that. In other words, that one could construct something that had all the characteristics of a balance, and then one had to obey rules that kept those characteristics. I think that comes even before the actual matter. The other question I had, and that's a question, whether people agree that that's an even more fundamental characteristic of an equation. The other question I had was, you were talking about the metaphorical transfer of meanings. What is it that the non-metaphorical elements, symbols, are about? I mean, when you have the physical interpretation, it could be hydraulics or it could be waves. But what's it about when there are no physical interpretations? What is it about?
Yeah.
It's sort of the question that I was asking, was taking a step back before you get to the metaphor. What is mathematics? Essentially, it's a construct of the human mind. It is the language in which reality is written.
Okay. Well, let's get to that. But there was another question back there first.
Essentially, it was replicating the same idea, which is that are we presuming and I got this feeling just when you were talking about mathematical metaphors and using those to. So when we say, time is moving forward, we're having access to a sort of mathematical concept. But I can't help but wonder, are we assuming that the universe does math and that we are then sort of describing it or accessing this math that's being done through our sort of metaphors and hence accessing math through metaphor? Or are we, because the sort of primary way that I sort of have been approaching math recently is that it is the closest approximation to predict how reality will behave in the future. And so those being competing, sort of math as metaphor.
That's a version of your question.
Yeah.
Okay.
Barry, I want to say something about that particular metaphor that is being far in the future. It seems to me the most peculiar metaphor in the world, because not only does it spatialize, it spatializes something that is not a space and that doesn't exist.
What's that?
The future.
Oh, the future.
Yeah.
Oh. Yeah.
Yes.
Well, we'll get to the.
Yeah.
Go ahead. Ask the question, and we'll get to the.
I want to point out in this connection that cosmologists like Brann Green are always interested in the question of why mathematics seems to describe the universe so effectively. They ask why. What is it about math that it should be able to do this? And if at some point in the evening, Dr. Brann, Dr. Mazur, you get a chance to just talk about that a little, I think it would be very interesting.
Why?
Okay. Well, okay. Look, there are various possibilities, so we can vote on this at the end. So I'll just give you a few of them. Okay. Here's one. Mathematics is, in fact, the way we construct our presentations of the world. It's the fundamental vocabulary of the way in which we piece things together. So if it's not amenable to that vocabulary, we'll never piece it together. So everything that seems to be such a beautiful fit is because it's almost the anthropic fallacy. Because that's how we think. And that's what we mean by explanation in the end. And anything that is amenable to this works. It's sort of like Freud at one... I think it's Freud. Freud...
Not the Freud police.
All right. All right. You correct me whether Freud was the person who said, isn't it amazing that the cat's fur knows where to put two holes exactly where its eyes are? I mean, there's a, we have a certain amount of a repertoire of explaining power.
Barry,
And
I'm going to interrupt you.
Yeah.
That doesn't explain enough. Because the question was, I thought the question was, how does mathematics happen to fit the world? And the fact that we think mathematically wouldn't be good enough if the world wasn't amenable to being thought about mathematically.
Well, how about those parts of the world that's not amenable to being thought about mathematically will escape us?
Yeah, but I mean that may well be, but it's still a question what it is about the world that makes it. I mean,
okay.
In some way it's obvious. For instance, everybody here is a unit, and that adds up to number. But in other ways, it's not so obvious.
But you see, you're really reflecting the two different points of view. One is that it's a construct.
Oh, yeah. I'm not finished.
One is this reflection of reality.
Right. We have to vote because I just gave you one thing. There's the absolute opposite view, which is that what we think of as the mathematics that we are constructing is really the architecture of the cosmos that we're observing. And we observe this, and we put it down in sort of a reasonable form. And of course it fits, because that is the faithfulness of our observation. So that's the Platonic view would be, we are observers of architecture when we're mathematicians. And when we carefully set down our mathematics, what we're doing is we're carefully setting down elements in elements of the structure of the cosmos. And so in the end, we take a look at it and we say, my God, it fits so well. Well, it fits because we are good observers. That's the Platonic, and the Kantian is the first thing that we could vote on. And there are other attitudes. And when you ask the question, I think it's much more interesting to ask the question and to weigh these possibilities, the pure Platonic against the Kantian, and see to what extent does it ring true, to what extent can one make sense of it, and to what extent does it lead you to further insights? Sorry, Barbara, I didn't want to stop you.
And what is your first explanation can't be right, that mathematics is the language of explanation, because you're talking words, not mathematics.
Yes.
You're explaining things in words, and that's just fine. And I think if you explained it in mathematics, we wouldn't understand it. When I watch mathematicians talking to each other about mathematics, they use words too. In fact, they use metaphors, mixing them. So, and then with regard to the question, I wanted to propose a sort of a third way, and that might be that we make the mathematics fit what we think the world is like. That mathematics isn't a single thing. There are many kinds of mathematics, many kinds of theories that can be incorporated in math, and we pick the one that seems to fit the world, which doesn't feel exactly Platonic. It feels a little different. And I don't know whether either of you would agree with that.
I think, we're mixing apples and oranges here. The apples, I don't know which is the apple, which is the orange, but one of these fruit is the question of why mathematics fits the world. In other words, why one can attach a mathematical formula to an event in the world, to be it free fall, be it of a situation of attraction, whatever the case may be. In a very simple sense, why can mathematics describe motions in the world? And the other question seems to me, and I don't think they're the same, where the mathematics that is pure and unapplied, that is the non-physical mathematics, comes from. Do we get that from the world? Barry and I were talking about Hume before. Hume is absolutely convinced that we get mathematics by observing the world. It seems like a kind of madness to me. It doesn't come from there. So aren't these different questions?
I think they're different questions, but I like the English. I like it very much. And so that's a third one which we should vote on. That, in fact, everything is language. I mean, our native language. And what we're doing is we're building on our native language in various directions. And one way of building, given the metaphors of space and number, really, and various other metaphors that are sort of the building blocks of mathematics, one way of working on language so as to sort of have enormous power is the mathematical way. And maybe what you're saying is we shouldn't distinguish this from other ways of working on language so as to have enormous power. And the root there is language. I mean, in the Meno, when Socrates asked the slave boy to essentially do a mathematical problem, he didn't ask what his background was in mathematics. He just asked, "Do you know Greek?" And the person said yes, and then he repeats it. "Do you know Greek?" He says yes, and then he's off. So it's possible that really your brand, that language is the root of everything, and that there are certain offshoots of language which require, again, sort of a focus of metaphor, correspond to a lot of things, including mathematics.
Yeah, but I keep saying but.
But, go ahead. All right.
That, on the one hand, it's true he's talking language all the time, and he usually does it. But it's also the case, the example that he mentioned, where they're trying to find what the relationship of a diagonal to a side of a square is. It ends in what is, I imagine, the most important set of numbers in our world, irrationals. That is to say, unspeakables. That's what the word means.
Oh.
Yeah. Say something.
Okay. Well, okay, there are lots of questions, so sorry. Happily, I don't have to answer that one.
But I think something that might be an 800-pound gorilla in the room, which I think is addressed by the point of language and the point of metaphor and the point of talking about systems, is that mathematics in some ways is describable as a system, and we know through Gödel that the system is limited. And yet somehow, through the paradoxes that we derive from incompleteness and the inability of a system to be so robust as to prove every statement in its own set true, that we can recognize it, and this is the point I've seen made, is that there's something about our abilities to understand phenomenal experience that allows us to appreciate the paradox without being able to explain it or to be able to solve why there is this limitation. So this, to me, roots back in the point you made about body and about the fact that as humans with perceptual apparatuses and conceptual processes, we are dealing with phenomena in the world which we have a certain kind of access to, and all of our processing seems to be predicated upon the kind of access we have to phenomena, whether they're in the world or in our heads. There's still this fundamental set of operations we are doing, and there might well be limitations to that set of operations that we can appreciate but not fully explain.
It's related to your question, yeah? That the minute you have a vocabulary, which you put in a system, if the system is sufficiently rich and reasonable, there will be questions that lead outside the system, that you can pose within the system, but you can't answer within the system. That's Gödel's discovery. That the minute you fix on a system, there will be something in that system that will break out. Okay? Right. With any such numerical issue, for example, you have the square whose sides are 1 and 1, and then you draw the diagonal. The first interesting line that you might draw in Euclid, and you ask, what is the ratio of the diagonal to the edge of the square? And you discover that if you're within the system of fractions, of rational numbers, you will never be able to answer that question explicitly in the terms of the system. So you break out of that system, and so you say it's irrational, but it's irrational relative to that system. But of course you build a bigger system where it's perfectly rational, although not by name, because you called it irrational.
In other words, you don't have words for it. You have a name for it.
Yeah. No, I have words for it, and I have a name for it. It's just not rational. Yes?
Well, I think we have to appreciate the order of phenomena.
Which phenomenon?
We have to appreciate the order of the phenomena.
Yes.
And just some simple facts. The universe, as we've calculated, is 15 billion years old. The Earth is 4 billion. And interestingly enough, the existence of the logic of natural phenomena predated the development of mathematics by billions of years, which leads to
the logic of, in other words, the processes predated our understanding of them.
Right, which leads to the conclusion that nature has been essentially dominated by sets of relationships that have a certain regularity. And when you look at mathematics that may have come into existence in the most primitive form 5,000 years ago, this was in some ways an effort to understand the existence of rules and relationships, and therefore we can say that mathematics is understandably related to the universe because it's partly a comprehension of the logic that underlie the way in which nature created things. And on one hand, we can feel very fortunate that there is a regularity in this world, that we do not have a kind of supernatural phenomenon where we're constantly confronted with the fact that every relationship between certain factors is completely irregular.
Right. I agree with you, but can I label what you say the efficacy of mathematical physics? But there is mathematics that has nothing to do with the natural world, and that's the type of mathematics that Eva was talking about, the mathematics that asks, is the ratio of the diagonal, the length of the diagonal of a square to its side, is that expressible in whole numbers? That has nothing to do with the natural world. Or pi, the circle, well, you could have either the area of a circle of a given radius, or the circumference of a circle of a given radius, and you ask, what is the relationship of that number, either of those two numbers, to the radius? And this, on the one hand, is a very unnatural question to ask, because we can approximate it. We can build wheels, we can build any approximation we want. But when we ask the mathematical question, what is pi, we are going beyond any approximation. It only becomes interesting if we make no approximation, or no, there are other interesting questions to ask. But the primary interesting question about the number, the square root of 2, or pi, these are highly unnatural questions, and what's baffling is how persistent these questions are, and how uniform a structure of explanations we have to encompass these questions. But equally, we have a uniform structure to encompass the questions of the natural world. That's a different...
Is this, that the universe doesn't have to absorb every mathematical formulation, but the fact is that the universe, insofar as we know it now, is fairly accurately described by various mathematical formulations. The further development of mathematics is still in the abstract, and whatever practical utility may be further discovered, but we can also be appreciated as just the mere development of a certain logic, mathematical logic.
How do you integrate quantum mechanics with that point of view?
Quantum mechanics, very satisfactory. It resolves subatomic phenomena in a very adequate way with predictable equations, and there's no difficulty. The problem is integrating quantum mechanics with relativity, which has been
Okay, now these are very lofty issues. There's relativity, quantum mechanics, and of course the full panoply of physical laws regarding the natural world, billions of years old. Let's go back to more primitively, let's say, let's say issues that we can personally sort of attest to, that we can have our own personal autonomy about. For example, the simplest constructions in geometry. Now, if you think of it, any time you have a question in geometry that requires a construction, the question never asks for the construction. The question asks something else. And the construction comes as a, let's say, a bolt out of the wilderness to change your conception, your own conception of the issue. So I have prepared something here, which is a very simple diagram. I'll find it. If I can. Okay, here's my little diagram. I drew it, so it's not perfect. What? Oh, sorry. I drew it, so it's not perfect, but it's two parallelograms. And it's meant to be two parallelograms of the same base length and the same height, but of different, let's say, different lean-tos, so to speak.
Can we see it?
Okay. Now, it's a fact, due probably to people before Euclid, that the area of these two parallelograms are the same. In fact, the area of any two parallelograms that have the same base length and the same height, these areas are the same. Now, how do you wrap your mind around this? How would you go about showing such a thing. And of course, if you know the answer, you know the answer. If you don't know the answer, then it's interesting, because you have to think, my gosh, this guy has shown me two parallelograms. They don't look like they have the same area. They don't even look like they have the same base length and height, but I measured them, they do, at least to the width of my pen. And so therefore they have the same area, and they certainly don't look like they have the same area. How would I ever do such a thing as to convince myself of this? And usually if you ask this question of yourself, there's the big question that you have not asked, that you will not have asked, which is, what is area? Okay? Right? Well, here's the construction. You take the parallelogram, and you draw a perpendicular to one of its sides. Now, what have you done? You've broken the parallelogram into some funny figure plus a triangle. Now you just move that triangle. So as to replace the parallelogram by the rectangle of exactly the same base length and of exactly the same height. So, what has the construction done for you? It has said that there is a process, cutting and moving. You have to make a construction, you construct a line, you cut, and you move the triangle over, and you've regularized every such parallelogram, and you've made it out of the same material, so to speak, as the rectangle. And so of course it has the same area. And when I say of course it has the same area, I've snuck in to the discussion a definition of area. Well, I haven't quite defined it, but clearly if I cut a figure into little pieces and move the pieces around and make another figure, those two figures are going to have the same area. Any construction like this has the effect of completely reorganizing the question it purports to answer. And this usually in a very, the construction is good, in a very powerful way. One of the problems in teaching mathematics is that once one does such a construction, one goes on to the next thing. Whereas one could spend 2 months on just this construction, because there's a lot to understand about it. Anyway.
When I do that with my 10-year-old,
good.
And we cut them up and we move them around, and they, and then they have no problem with the formula and they love it and everything. But the thing they don't understand is why I get so bent out of shape if they don't put square units in their answer. And I keep trying to explain, but it's a little surface. It's a two-dimensional thing, and that is the thing that they figure out that I get bent out of shape. But that's the thing they don't really get. Why the square units?
Well, that's the stealth issue in this whole thing. Just out of drama, you don't define area to do this. Because if you did, you'd be spending a week defining area. What you're doing is you're setting up the situation where it will eventually become absolutely clear to the student how to define area, given that this is the process that that identifies two figures of having the same area.
But you've run an end run around the question of the definition of area.
Yes.
And instead, you've shown what equal areas are.
Exactly.
Yeah. How, incidentally, if it becomes clear what an area is, what is it?
What is an area?
Yeah.
Well, that's it. Okay. Here's a thought. You give me your most favorite figure.
As you know, that's my favorite figure.
The rectangle.
The one, the way I think of it is it's between rails, right? And you can take it and pull it as far as you like. It's thinner and thinner and thinner. I don't know if your students do that. It's a lot of fun to do. You just take the rectangle or parallelogram in the area, you keep the base fixed, you take the top, which is equal to the base, you start pulling it along, and you pull and pull and pull, and the thing gets thinner and longer and longer. And my guess is, weren't you telling me about someone who studies how people are fooled by mathematical, this business about 8, 7.
Oh, okay, yeah. I'll tell you about that.
Tell us about that.
No, but go ahead.
But I was going to say, this seems to me a similar case. People think that because something is long, it's got to be larger than something which is short. And it's I love that. It's beautiful.
But you're right. I made an end run around the definition of area, which is.
But explain I mean, just because it's
okay.
So nice,
Well, this is in the context of our intuition sometimes fool us, and Amos Tversky was one of the great scientists who developed a number of, let's call them experiments. They're experiments that he did with a number of subjects, 50 subjects, let's say, but they're very, let's say, personable experiments. You can do it to yourself. And you're as convinced, if you do it to yourself, that there's something strange about your intuition, in the case of elongated figures having larger area, that's one, but the other is in numbers. So here's a test, which I'm going to ask you to make a guess, but the guess can be totally private, so there's no shame. Okay. And don't take out your calculators. You have to guess. Okay? What is this number? Guess the number. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? Secret guesses. Everybody, but you have to have a number in your...
1 multiplied by any number.
What?
What is 1 multiplied by...
No, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, and you can multiply it by 1 or 2 if you want. Okay? Everybody make the guess.
Right.
And now, if you've made the guess and it's wrong, you're not alone, by the way. Okay. So Tversky would give this as a, ask, say, a certain number of subjects, let's say 50 subjects, and he would tabulate their guesses. And there's an average guess for this experiment, and I'll call that average guess X. I don't remember what it is. Then he would take 50 other subjects and ask them a completely different question. I'll tell you the different question. Yeah, you see what it is. 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. And the 50 subjects will write down their answers. And there'll be another answer, average, there'll be sort of the mean, would be Y. And Y is significantly smaller than X. And by the way, X is significantly smaller than the true answer, which is 3.5 million, roughly. So, we are now. Amos Tversky had a category for this. He called this framing, I believe. And that is to say, when we're asked the question 10 times 9, we're thinking big number, big number, big number, big number, even though it's going down. And even though we could rationally sort of regroup and reassess at the end of the description of the number exactly how big a number it is, the fact that our first impression of it was that it was big, 10 times 9 times 8 times and so on, influences our sort of rapid estimate of the number. And if we started 1 times 2 times 3, well, we'd think small number, small number, small number, and that influences the outcome as well. So one of the things that I guess we began this discussion with, that the intuitions of mathematics reside to a large extent in the body, or at least sort of are related to aspects of our physical being, of our physical intellectual being, so to speak. Here's another example where we have a kind of hard-wiring predilection to favor the beginning impressions of something, even if it is as abstract and as objective as a number. You know? So I mean, that's what Eva wanted me to recall.
Back to area.
Yeah, okay, go ahead.
Suppose I call the answer n factorial.
10 factorial.
Do I know that number? I mean, is just calling it n factorial and calling it 3.5 billion, is the 3.5 billion more knowable than the n factorial?
I actually wrote down what it is. I don't remember what it is. Is it more what?
Is it, if I just call it and give it a name, do I know that number?
Okay.
Why is 3.5 billion make it more, quote, knowable?
Yeah.
Is it necessary?
No. Okay, that's a good question. The thing is, what is knowable depends upon one's own prior vocabulary. And so we very often are much more comfortable with decimal notation than we would be with, for example, binary notation. So if I gave you the answer in binary, you might say, do I know this? Well, what the? And why is that any different from just saying it's 10 factorial? On the other hand, to compare two numbers, some systems are better than others. And so I was interested in the comparison and the size of it. So if I said to you, 2 to the 10 minus 1 or something, you would have difficulty comparing it to something like 3 to the 8th plus 5. More difficulty than if I put it in decimal notation. And so every way of expressing something in vocabulary puts a spotlight on some things and allows you to do certain things easily, and other things less easily. And that's,
in this case, it seems to me that the reason that 3.5 million is somehow more substantial than 10 factorial is that 10 factorial is an invitation to do an operation, and 3.5 million is an outcome, and I like outcomes better than I like operations.
Don't I have to multiply 1 million by 3.5?
So numbers related to fingers.
Uh-huh.
You from the earliest stage, you relate to
digits.
Yeah. Sure. Yeah. Okay, let me see. I've got lots. Yes.
I find that most people cannot comprehend the size of large numbers, and I think it explains a lot that goes on in politics. A nice question to ask people is how long they think 1 billion seconds is, and have people make a guess of that, and then if one's teaching children, you might have them actually do the calculation. And it helps one realize how much we can't really comprehend what 1 billion means. Maybe much more than...
Yeah, that goes back to your question, right?
Yes.
I mean, that maybe 10 factorial for certain people would be more telling than 3.5 million. And we have a difficulty really coming to grips with large numbers, absolutely. Yes?
I mean, it seems we have an impulse to grasp something concretely.
In other words, as actualities as opposed to realities, which are accounts of things. So if we're talking about area, it's fairly easy to say what the area is, but it's very, very difficult, probably impossible, to know what area is. Because that's the concrete question.
Okay, Francis, yeah.
Barry, I just think that's sort of stupid, but when you showed the diagram, right, I was trying to figure out, I was trying to figure out how I was going to approach this. So I said to myself, angulation, that's it, angulation. And I think that's what's wrong, that one tries to find one variable. And I thought, well, the sun rises, at varying angles. And I was trying to I immediately tried to figure something out, but I was limiting the possibility in order to comprehend what you were trying to get at.
Well, there's also first, that's true. Secondly, it's inevitable, and sometimes there's strength in limiting a possibility for a short time, so to speak, and being willing to change if it doesn't work. I mean, I have an example, but there's another question which I'll get to later. Yeah.
It's not a question really, but in thinking about what is area, is that any different from what is free? No. There's a freeness about stuff, and there's an area about stuff.
Well, the thing is, I would have to, if someone sort of held me here to it and said, define area, I know how I would do it. But if they then say, what is area, after I define area, that's a philosophical issue which I don't think my definition would approach. Let me just say how I would do it. Take your favorite template. So anything you want. It could be a square. It could be a little disc, a circle. And you allow yourself to change, to zoom in or out with it. And now you take many of those templates. You call those templates, that whatever template you choose, you call that a unit. And you try to cover the object with those templates. Now the covering is not exact because there's overlap and it's just terrible. But you do it and you make a count of how many of your units you needed to do it. And now zoom, make it smaller and cover by exactly the same and make the appropriate computation and continue ad infinitum until you approach the actual area of the object. That's one way of doing it, and I like that way. But that doesn't answer your question, what is area?
No, and it's not unlike saying how would you define the square root of 2, but again, as a limit.
Exactly.
It's the same kind of thing.
You had a question?
I don't want to perturb the thread of this, so if you reject the question, it's okay.
We wouldn't reject the question.
It's kind of relating to to an emphasis more on the process, which you seem to enjoy more, and body. Many years ago, when I was a math major undergraduate, so don't ask any hard questions, I was amazed at the following phenomenon. I'd be working my butt off all night trying to get the answer, trying to get a proof. Couldn't do it. I got up in the morning and it came like that. The same process. I guess it's related to body. The same process occurred many years later when I became a computer programmer. I would work all night on something and could not see it, could not see it. Go away, step outside the building, and it would come again. Is this an imaginative leap? Is it, similar to Pascal in his Night of Pascal, the mathematician, in his Night of Fire, when he made the leap to faith? I've always been, why can I work all night on something, go to sleep, and then next morning I see the proof?
But you couldn't wake up the next morning and get it without having worked all night. Could you? We have a secret workshop that keeps going.
Just on that point, I mean, that brings to mind, how much of what we're doing with mathematics is related to consciousnesses. Are we limited by our experience? And if our brains are processing these operations without our conscious experience doing it, doesn't that beg an interesting question, which is why are brains doing this? What is it about the organization of a human organic brain that seems to be able to do this without even the subject involved? And I think
I have a colleague who a couple of days ago told me that there is a line in Plato's Republic. I sat up far too late last night trying to find it. I don't think it's there, but it's wonderful. Whether it's there or not, it said that he claims it says that mathematicians tell while awake dreams that they had when asleep. That's what mathematics is. You like that?
I like it, yeah.
I don't know what it means.
I wanted to ask you, to what extent has mathematics taken psychoanalysis as a fitting subject to explore in order to make some systematic efforts to develop some rules, and taking into account the fact that the average mathematician would probably not know very much about psychoanalytic phenomena, the formation of the psyche, the id, the ego, things like processes like transference. But nevertheless, since the human mind and personality operate according to definite rules that we've clinically validated, to what extent did mathematics seem fit to attempt to systematize?
Oh, I think it has systematized it.
Pardon me?
I think it.
Well, could you point to particular...
Well, with Barbara's addendum, that is to say, mathematics is based in language, and to the extent that one talks about psychoanalysis, one uses language.
I think Freud's work on negation is much to the point. Does that ring a bell? He wrote that famous little article on negation, which essentially explained what it means to have, among other things, negative numbers, negativity of any sort. I think that's the case. Yeah. Does anyone remember that article?
There's a value of mathematics with more for predictability. In other words, if the patient concentrated on certain aggressive feelings towards its mother, then one would be able to make a prediction as to what degree this would appear with certain frequency.
Well, it hasn't been done, of course. And
why not?
No research funding.
Okay. All right. There's one. I think we might be coming to a. Oh, sorry.
So I was going to give you a choice to return back to why math fits the world, or a move towards mandalas, geometric sort of visualization, and the sort of very esoteric tradition of using mathematical imagery as a spiritual and meditative path. So you can.
That's interesting.
But if you
I see. Okay. So you're.
I'm giving you.
Well, you're pulling me in two completely different directions. Okay. In other words, let's go back to the vote, which is whether mathematics is yes.
Oh well, if we are going I just wanted to add one thing to the vote, which was the option of why math fits the world, because we invented it that way. The idea that it was collectively pruned as an idea that evolved over time, with the constraint for that pruning being reality. So we evolved an idea to meet reality. And so the example you gave was of the square, for example. You have 1 and 1, you have a system, and you say, well, we hit the constraints of our system, so we invent something to then allow us to keep progressing. And the reason we invented is because we hit a constraint based, and the constraint being arriving from reality. So obviously we end up with something that very neatly explains reality, but that's how it came into existence in the first place. You see, the collective pruning of this idea over centuries, over millennia, was in response to the reality constraint.
That's interesting, but that's okay. That's one part of the vote. So let me organize the possibilities so far. One is yours, which was in a sense there is the structure of our mind, and the structure of our mind sort of describes constrains, if you wish, what we call explanation. And if we systematize the types of things that seem to have objective explanation for us, given the structure of our minds, we produce mathematics. That's one way of framing it. The other is the Platonic way, which is we're simply describers of the architecture of the cosmos, and we describe it very well, and so therefore it fits. The third would be that we're very good analyzers of ourselves. This is almost a psychoanalytic one. That the minute we say something that claims to be causal or claims to be explanatory, we analyze that and we formalize that into a kind of logical and then super-logical structure which produces mathematics. That's in the direction of the what is sometimes called the formalists.
How is that different from one? The first choice.
The difference between that and one is it's partly cultural. Right? I mean, it depends upon, it has nothing to do with the way in which we have to explain things. It's just a kind of a cultural buildup. And so those are the three standard ways that people talk about. And I like the idea of voting because sometimes if you look at a piece of mathematics, you say, yes, it's culturally dependent. You look at another piece of mathematics and you say, this is the architecture of the cosmos. And you look at a third and you say, this is the way in which my mind works. And there's no way of, I think, coming definitively to any conclusion here, but there is a way of respecting the whole thing as something that is going to be with us as long as we do mathematics, this voting, so to speak. Yes?
Can I blur at least one distinction here? The distinction between the Platonic idea of the irrational number and the natural world. In at least one respect and on one level, as we know, there are many examples in the natural world of things that seem to be aware of 5. The golden ratio.
Oh, okay.
That ratio. We see it in the Nautilus shell with its logarithmic spiral. And we see it in, for example, the spirals of a sunflower and its seeds that seem to have Fibonacci pattern in them. I just wanted to throw that out there.
That's actually right. There is the natural world pushes some very abstract mathematics on us. That's basically what you're saying. That you just look at a sunflower seed, and all of a sudden you're beginning to think of 1 plus the square root of 5 over 2 for some funny reason. And I like that. So those are 4 things. Yes?
I don't think that's quite right. You can think of rational numbers that are close to 1 plus.
Yeah, I know.
In the natural world, the diagonal of the square is 1.41 something or other.
And a 2 by 4 is 2 by 3 1/4 apparently.
That's something that I learned to my dismay once.
Oh yeah, everybody. That nail in the floor tells it.
But I think that the Platonic point is not recognizing the natural world. I think the mathematician, or that mathematics, recognizes the natural world as it ought to be, but not as it is, as some sort of a purely
realized world. I shouldn't have said realized. That's
You shouldn't
exactly.
have said ought to be, but by the way. But okay, yeah, you certainly feel that sometimes, yeah.
What would, of these three ways of dealing with the, what would St. Augustine have, where would he have fit? If I recall, it was something like, if you ask me what time it is, it's 8:15. But if you ask me what time is, I don't know. I believe he said something like that.
I think he said, if you don't ask me what time is, I know it.
I have to tell you what Yogi Berra said. Who said the best thing that was ever said about time is that I've read. Someone asked him what time it was, and he says, "You mean now?"
Well, I think it's time to come to an end, but I want to thank. Oh, well, okay. One quick question. Okay, right. Yeah.
Before you leave, I want to ask you.
Yeah.
Can the language of personal relationships be transferred to mathematics? For example, do you like, or some of your best friends, some of the mathematical objects that you work with? Or, do you have affection for certain mathematical objects that you create?
Doesn't everybody have an affection for things that they are working on, that they're obsessing on? I mean, if you think of, well, yes, yeah. I mean, certain
natural human tendency.
Certain numbers, like the number 37 and 691, are my favorites. I mean, they really are, in some funny sense.
Just a small comment. I'm an artist, and I would like to get attention to, for example, this chair, how mathematical it is. It's a little bit more simple mathematics than, for example, shapes in this room. And probably this goes to conclusion that our brain, drawn to mathematics much more than, for example, real nature. When we go to real nature, we rarely see the straight line. Although here we should blame mathematics that we live in these structured and all square buildings.
Frank Gehry will not have it that way.
Excuse me.
I don't know. Should we? Okay. What?
I'm going to try and phrase this properly. I'm way out of my league here. You discuss the natural world, and then you discuss the human brain. And you seem to make a distinction. Is that, how do you derive that distinction? Is it philosophical? Is it not? Where does it come from?
It's a good question. Okay. Well, let's have a spectrum of something which is not real, and that's your question. And you're going to say that this whole spectrum is not real, but I'm going to make the spectrum. Call it the objectifying spectrum. So at the very end of the objectifying spectrum is volcanoes and things like that, which I can talk about and measure. And getting closer to it would be my blood pressure, right? And then closer to that would be maybe my, this is anybody's, brain issues, which, of course, they're objects. They're not us. Now, the natural world is somewhere there, and the psychological world is at the very far end of the objectifying spectrum, that is to say, the unobjectifying end. And I wouldn't want to make a clear distinction except workable ones, usable sort of ad hoc distinctions to be able to say, yes, sometimes it's my thought, and sometimes it's the natural world that I'm sort of developing mathematics for and with, or by means of. And I don't want to make the distinction very precise. Is that, would you agree with that, Eva? Or not? Probably
well,
not.
To me, it seems that there really is a fairly radical distinction, a real break between beings that reflect and the beings that don't reflect, sticks and stones and universes. I have this feeling that aside from fictions and dreams, the world doesn't think about me, but I think about the world. And that seems to me a very deep difference between thinking, being a subject, being an ego, a human being, and being a world. So I think that there really is a distinction. You can give any number, a large number of criteria for what it is to be a thinking subject, which is the usual philosophical term for a thinking being, and being the world out there. Of course, in that world there are other thinking subjects, and a great issue is whether it's just human beings or possibly also animals. Yeah, but that, I mean, that's not the main issue.
But I'm not sure that goes to the point of that which is natural. Is the human being natural? If so, then, and if not, what is he or she? And if so, are not the parts of the composition natural?
That question seems to me complicated by the fact that there are two distinct meanings to natural. There may be more, but two that get involved in your question. One meaning of natural is given. Is it made or is it found? And I think human beings aren't made. Well, I mean, there may be religious aspects to this, which I'm leaving out of it, but found. And that way, human beings are natural, and their thinking is natural. But the other meaning is that is natural which obeys laws. Maybe deterministic, maybe probabilistic, but obeys laws and has to obey them. And I don't think I need to do that. In other words, I think I'm to a certain degree freer than what we call nature is. So these are the two different ways of thinking of nature, whether nature is deterministic or probabilistic, but law-governed. I'm not law-governed. Well, I don't need to explain to you why I'm not law-governed. Yeah.
So,
answer.
Is evolution, which is a process which presumably we come out of, is evolution law-governed?
There's a huge debate about that, whether evolution is in fact a theory of law or of observation. It can't predict, so it doesn't have the characteristics of physics. So, I mean, that gets us into a really interesting question. But
okay, that's a good way to end our discussion.
Thank you.
And thank you all for
Further information about our programs and a complete archive of past Philoctetes events is available at philoctetes.org.